Okay, good morning. Welcome to the 2022 annual TK Cheung lecture in animal science. My name is Cheung, associate professor in the Department of Animal Science at the University of Manitoba. I'm the chair for today's seminar. The University of Manitoba campus are located on the original lands of the Anishinaabe, Cree, Oji Cree, and Dakota, and the Dani peoples. And on the homeland of the Métis Nation, we respect the treaties that were made on these territories. We acknowledge the harms, mistakes of the past, and we dedicate ourselves to move forward in partnership with the indigenous communities in a spirit of reconciliation and collaboration. This annual lecture recognizes and honors Dr. Stan Cheung and due the support for the Department of Animal Science and the Agricultural Research at the University of Manitoba. Dr. Cheung obtained his BSc and MSc and a PhD in Animal Science from the University of Manitoba. His graduate training was in animal breeding and genetics under the supervision of the late Dr. Bob Parker, and he was also awarded a Doctor of Laws from the University of Manitoba in 1991. Dr. Cheung retained his family business in Hong Kong in 1975, and he is currently the executive chairman, director of the Harrod Holdings Limited. Dr. Cheung's many contributions include support of the TK Cheung and Center for Animal Science Research, and the National Center for Livestock and the Environment, and the TK Cheung Reading Room, and the recent contribution to the education and the research in animal science. In recognition of his generosity and the commitment to the education and the research, the department established its annual seminar in his honor. And today we are very happy to have Dr. Weiss, and Dr. Weiss, Professor Emeritus in the Department of Animal Science, Ohio Agricultural Research Development Center at the Ohio State University. Received his BSc and MSc degrees from Purdue University and his PhD from Ohio State in dairy nutrition. Throughout his career, his research has a focus on forage utilization by dairy cows, relationship between the minerals and vitamins, and the health of dairy cows, that formulation variability and fresh cow nutrition. And Dr. Weiss has authored or co-authored 2 books, 13 book chapters, 143 peer-reviewed articles, 104 abstracts, and 262 popular press and proceedings articles. And his paper has been cited over 7,500 times. And moreover, he has 20 papers that have been cited over 50 times, particularly documenting his railroad expertise in the energy, vitamin E, and selenium nutrition. He had delivered over 285 invited national and international talks. He has received many awards based on national and international excellence, including 3 research awards from the American Dairy Science Association, culminating in being named an ADSA Fellow. And Dr. Weiss' presentation today is incorporating variation into diet formulation for dairy cows. Please join me in welcoming Dr. Weiss. Yeah, the floor is yours.
Well, thank you very much. It's quite an honor for this invitation. Let me share my screen here, and then does everything look okay?
Yeah.
Okay.
Great.
Well, I visited the University of Manitoba my first year as an assistant professor at North Dakota State University. That was my first job. And I was looking forward to visiting your campus again because it's been 35 years. But with COVID, we've all learned to be very flexible. But again, thank you for the honor of inviting me for this seminar. What I'm going to talk about today is something we started right at the end of my career. I'm wishing now we would have started this research earlier, because it's quite an interest to me, and I thought hopefully I'll make it an interest to you. And that's basically, how do we use variation in feed and animals when we formulate diets? What we typically do, let me just get my pointer. When we formulate a diet for dairy cows, and this is the same, well, I'm ahead of myself. What I'm going to try and talk about today is, first of all, understanding variation, and specifically understanding sources of variation. I want to talk about how we can get some estimates of variation. And then part of what I'm going to talk about can be applied today. There's ways we can use variation today when you formulate diets. But there's also a lot of research that needs to be done. So for the students in the audience, I'm hoping I pique some interest in that we can develop research protocols to start using variation better in the future. And these topics will be interspersed. They won't be discrete categories. But when we formulate a diet for dairy cows, and this is the same for beef, I'm not familiar with swine and poultry, but I think it's probably similar for all species. We'll sample the feeds, and often for dairy, all we sample is the forages, and we send it to a lab and get a number. Or you might be a nutritionist and you're collating corn silage for your region, so you have the average for your corn silage or whatever. Or very often you just go to the book, a table, or the software and get the standard composition data. For the cow part, depending on what you're doing, you might, if you're a research, you might enter data for a single cow. If you're formulating diets in the real world, you might take the pen mean, the average body weight, average milk production, average milk composition for a pen. Or if you're feeding a single diet to the whole farm, you're going to use farm means. And then basically you're going to go to whatever software you choose. It's going to use linear programming to get a diet that meets those requirements. The diet is based totally on either single samples or means. The cow is going to be based, or the cow data is going to be based on means. Everything is means. And there's no place in any of this software, in the software I'm familiar with, where it says what's the variation in the composition, or what's the variation in the requirements. And so I'm going to talk about how it's important that you start considering variation in both feed or diet and the cow. And again, some of this will be future things you need to think about in the future. Some of it will be things you can use today. Okay, so we'll start with the feed, and then we'll move to diets and then to cows. So why is standard deviation or variation in feed nutrient composition important? Well, first, and this can be, it should be used today, is variation in nutrient composition affects economic value. A highly variable feed is worth less than a consistent feed. Even if the average composition is the same, a variable feed should be discounted. And I'll go into more detail on this in a bit. We can use variation in nutrient composition of feeds to produce what I call semi-quantitative safety factors. And this is semi-quantitative because there's still some things we need to learn. I'll give some suggestions, but these should be adjusted as we get better data. And then lastly, poultry and swine, or at least poultry and maybe swine, use some nutritionists use what's called stochastic formulation rather than simple linear programming. This is, to my knowledge, not used in dairy at all. I'm going to talk briefly about this, but I think this has great potential, and down the road, as we generate better data, this may become the standard. Right now, it is not used in dairy. This is most of the histograms I'm going to show and actual data I'm going to show in this seminar is real. It's data we've collected. These are not made up histograms. This is the crude protein composition of two sources of distiller grains, A and C. I took B out just to make it a little less cluttered. A is highly variable. C is a fairly consistent source relative to crude protein. On average, they are essentially the same. They both have essentially 30% protein. So on average, they're equal. And I'm going to assume that fat and fiber and so on, energy, are all on average the same. But on average, they're the same, but economically, you should pay substantially less for distiller feed A, distiller grains A, because it is variable, more variable. And the reason it's worth less is there's going to be a lot of times you're going to get a load of distillers that's quite low in crude protein. And if you don't do anything, you just keep using 30% as the mean, those days or weeks when you use this low protein distillers, the diet will be deficient in protein, and theoretically you should lose milk. On the other hand, when it's high in crude protein, you get no benefit because you decided that 30% meets the requirements of these cows. So feeding more protein has no value. Feeding less protein loses milk, so you lose money, and feeding more protein than what they need is a waste. So there's one reason the highly variable feed is worth less, is it increases the risk for deficiencies and lost milk. The option then is, okay, every load of distillers I'm going to get, I'm going to analyze it and reformulate my diets. And that will prevent these deficiencies. But there's a cost. There's a cost to sample, there's a cost to analyze, and there's a cost to reformulate. You don't need to do that if you're feeding distiller C. If you're feeding A, you'd have to add this cost in. Or lastly, you might say, well, I don't want to do all this reformulation. I don't want deficiencies. So I'm just going to feed a higher protein diet. I'm going to overfeed crude protein, which is a wise decision, but it's still a cost. Overfeeding usually costs less than deficiencies, but this costs more than if you fed distiller C. So high variability reduces the economic value of a feed, and it should be fed or sold at a discount or purchased at a discount. This is again real farm data. We sampled several farms in an experiment we did. We went out not every day, but several days, measured in this histogram. I'm showing crude protein. Excuse me. And there's two farms here. One is what I'm going to call a fairly consistent farm. That's the red one. And then the green one is a more variable farm. On average, both these farms formulated to the same crude protein. But this green farm, the more variable farm, it's going to have a lot more days where there's an increased risk of being deficient. And if I was the nutritionist on the green farm and I couldn't work on reducing variation, which should be the first goal, but let's say I couldn't do that. If I was the nutritionist, I'm going to say, I've got to prevent these deficiencies. I don't want to lose milk. So on this green farm, I can't feed the same level of crude protein or calcium or whatever nutrient you want. I have to feed more. I have to oversupplement to prevent deficiencies. And that's exactly what they do. And these are just examples here. For the green farm, it's the same basic cows. Everything's about the same. This nutritionist said, okay, I'm going to formulate to 17% rather than 16% and equalize the risk of deficiencies. And that's a wise decision. But it increases the waste of protein, which is an economic cost, and it's an environmental cost. So this is what a lot of people do. They just say, I'm going to be feeding variable feeds. I'm just going to over supplement. And this is better than not over supplementing because you want to prevent deficiencies, but this is not the wisest thing to do. A much better approach, and this is something you can do today, is to discount feeds, base the overfeeding on the specific feed. We came up with this based on simulation data. And first of all, there's a few, this is why I'm calling this semi-quantitative, because I start this bullet with for variable feeds. And you should immediately ask, well, what's a variable feed? And the question is, I'm not sure. Just things like soybean meal, corn, canola meal would not be considered variable. So you could look at the standard deviations for those feeds as a coefficient of variation. And maybe if you are feeding feeds that have substantially more variation than that, you should apply this approach, but not for these very consistent feeds. And I'll go in a little more detail in a bit. But for feeds that you consider variable, you should discount the protein and macro minerals, nothing else. This is not discounting energy. You're not discounting or changing starch or fiber or the micronutrients, just protein and macro minerals. And the discount we've come up with, and again, this needs additional research because this is all simulation, is you take 1.8 standard deviations times the proportion of nutrient that feed is going to supply. And in this case, you're formulating a diet, so you don't know exactly, but you might say, I think distillers in this example will provide about a fourth of the protein or whatever you think it's going to approximately supply. So in this example, the distillers had 30% crude protein. It had a standard deviation of 4. And I said it's going to provide about a fourth, 25% of diet protein. So 4 here times 1.8, which is here, times 25% of the diet protein. And so what I would enter when I'm formulating the diet is for the crude protein concentration of distillers, I don't type in 30. I type in 30 minus this, which happens to be 1.8. So at the formulation stage, my distillers won't have 30%. It will have 28.2% crude protein. And this will adjust for this variation. And it's much more quantitative than adjusting the entire diet. You will feed elevated protein because this, on average, the distillers has more than 28, but it's discounting the specific variable feed rather than the whole diet, and it takes into account inclusion rate. Now we limit this to protein and macro minerals because the other nutrients, there's risk of both overfeeding and underfeeding. Protein within reason, it's not overfeeding protein within reason is not going to hurt the cow. It's an economic cost, but it is not going to hurt the cow. Overfeeding macro minerals within reason is not going to hurt the cow. But for things like NDF, there's risk at too high of NDF, you hurt intake in milk, but at too low of NDF, you increase risk for acidosis. So the nutritionist would have to decide if I really want to prevent acidosis, I might reduce NDF by this using this equation in the feed. But if you're really worried about lower milk production, you might actually increase the NDF by this amount. Or you might decide I want equal risk and not make any adjustment. So for nutrients other than protein and macro minerals, the nutritionist has to decide what risk he's willing to take. But this is something you can do right now and this gives you an idea of what the economic value is of variation in specific feeds. Stochastic formulation, which again is not used today in dairy, but right now what we assume with the programs we use we set risk at 50% because we use means. So if you formulate a diet for 16% crude protein, half the time the diet's going to have less than 16% and half the time it's going to have more. So you're saying you're willing to accept a risk of 50%. With stochastic programming, you decide what risk you want. This is the nutritionist decides this. And in this example, I might say, well, I don't want protein to be deficient. So 80% of the time, I want this diet to have at least 16%. So this would be set by the user. This risk is set by the user, as is the specification. And then with stochastic formulation, the user picks the risk, and it's the calculated diet is based on the variation in nutrient composition of the ingredients. So it will say, based on these variations, these standard deviations, this is the diet you need to feed to have an 80% chance that it has at least 16%. And again, this isn't used today in dairy. I think it has great potential if we can get good standard deviations. So that brings us to this statement here. All these things I've said I think are great and wonderful, but for you to use any of it, you need good estimates of standard deviations. I'm going to put a plug in for the new NRC, which is now called NASEM, Dairy NRC. It has a feed composition library, which is very, very good. We spent a tremendous amount of time working on that library. And one thing we really emphasized or tried to do is to get accurate standard deviations. So I'm going to say, I think right now, some of the best standard deviations on nutrient composition is found in that book. Corn silage, there's about 500,000 observations, screened observations in the data set. It has a mean of NDF of say 41%, standard deviation of 4.8. So you have a good estimate of standard deviation, but that's a population standard deviation. So, and that's not what you want. Because you got to think, okay, why would these 500,000 corn silages, why would the NDF vary? That's the question. Well, there's farm to farm, there's hybrids. You can think of hundreds of things that differ between farms why the corn silage would differ. There's a big one here, and that's sampling. The feed may not vary, but samples can vary because of poor technique, poor sampling protocols. Lab, if you analyze the same ground, if you take 10 samples out of a jar of ground corn silage, you're not going to get 10 same answers. They're going to be a little bit different. That's analytical variation. Then there's this time factor, and it could be load to load, field to field, cutting, season, etc. So there's lots of reasons feeds can vary. When we look at the diet, which is really what we care about, diet can vary because of variation in the feeds. It can vary because of sampling and analytical, and TMRs are extraordinarily difficult to sample, so you have a huge amount of sampling variation. Also, TMRs vary based on how you make it and how it's mixed, which if it's done correctly, TMRs reduce day-to-day variation. If it's done incorrectly, it increases it, and I'll go into that. And then lastly, you have the cow factor here, that they can eat what they want, which we haven't figured out how to include that variation. We did a large study a few years ago from 50 farms in the US, across the US. These were not just Midwestern farms. I won't go into all the details, but we had numerous feed samples taken, and we partitioned the variation in nutrient composition for farm and sampling and analytical and time. Or month is what we used. And what we found for forages and all wet products, wet byproducts, farm was significant source of variation. And what that means is you cannot or you should not use the population standard deviation. So you don't want to go to NRC and dig up the standard deviations for corn silage, because a lot of that standard deviation or that variation is farm to farm. And if you're feeding a farm, you don't care that another farm is different. You only care about the farm you're feeding. For several concentrates, this is soybean meal, this is dry corn gluten feed, we had canola, soy, whole cotton seeds, that farm wasn't significant. Use the standard deviation, and in fact, you can actually use the nutrient composition in good tables of nutrients. You don't need to spend time and money sampling these feeds. And then lastly, we have dry distiller grains. It's in its separate category because it often was. It wasn't consistent, but very often farm to farm had an effect. So on distillers, you use the standard deviations in books with caution, because there is at least a substantial amount of farm to farm variation. What we also found then is, because most farms are not going to have enough samples to get good estimates of standard deviations. You might. I'm going to encourage nutritionists to sample frequently enough and collate this data to get good estimates. But if you can't do that, we came up with a way to approximate standard on-farm standard deviations. And this was based on this paper we published several years ago. What we found was that on average, 45% of the variation in alfalfa silage was farm, 65% of the variation in corn silage was farm, and for a blend of, or a mix, or for a variety of dry concentrates, it was about 25% of the variation. So if you need a local standard deviation, and that's the standard deviation you should use for a farm, an approximation is to take the population standard deviation. So you go to NRC and look up corn silage and find the standard deviation, square it, because we're working with variances. So you'd square that standard deviation. And then if it was alfalfa, you'd multiply that squared standard deviation by 0.55, then take the square root of that, and that would be your best estimate of the standard deviation for alfalfa silage that you're feeding. For corn silage, you'd multiply it by 0.35, and for concentrates, 0.75. So that's, again, the best we can do right now. Okay, I want to talk about, again, back to sources. This is real farm data. This is from a farm that was feeding baleage. And there's 6 bales, and we sampled these 6 bales, and these are the NDFs we measured, ranging from a low of 37 up to 50. And you're going to say, boy, that's really, really variable, and it is. But you need to think, how are you going to feed these bales? If, for example, on Monday, the farmer took these 3 bales, put them into the mixer wagon, and made a TMR with, corn silage, etc., the variation in these 3 bales is huge. It's 6.8. The average was 44.7% NDF, with huge variation. But to a cow, this variation is absolutely meaningless, because a cow is not going to just eat this bale or this bale or this bale. It's going to eat a blend of all these bales. In this example, this is sampling variation, and it's meaningless to the cow. What matters to the cow is day to day. So these 3 bales were fed today. These 3 bales were fed tomorrow. The diet hardly changed. 44.7, 44.3. That's a trivial change. So sampling variation was huge, but day-to-day variation was essentially nil. So it's important to separate sampling from actual variation. If he only fed 1 bale a day, then these are the variations that matter. So it's really important when you think about how the variation in samples, is it real or is it sampling? And again, I'm not going to go into details here, but we did a total variation is farm to farm plus sampling plus analytical plus what we call true day to day. And you can partition this if you take enough replicates. So farm to farm, you sample multiple farms. Sampling, you take multiple samples per time. Analytical, you analyze things in duplicate or triplicate. And for day to day is basically everything left over. So we can measure all this because of if you replicate things enough, and then what's left is called true day to day. And we did this for several things, but we concentrated on corn silage and hay crop silage. And most of our hay crop silage is alfalfa or alfalfa grass mixtures. And over a 12-month period, we partitioned all this. And for corn silage, if you look at, this is the sampling and lab variation. This is what we would say is true month-to-month variation. And for fiber, it's the same. Sampling variation is as big as month-to-month variation for corn silage. So that's saying, you know, when you get two samples, you're as likely, and if the numbers from those two samples are different, it's as likely to be caused by sampling as it is by a true change in nutrient composition. Dry matter is more, there's more month-to-month variation in dry matter, and that makes sense because these are mostly bunkers and it rains once in a while. So on these feeds where there's a high sampling variation relative to true variation, it's saying take duplicate samples, but you don't have to sample as often. For alfalfa, there was substantial month-to-month variation relative to sampling variation. This is telling you you need to sample these feeds more frequently, but you don't necessarily need duplicate samples. And that's pretty much what we came to recommend. And you need to think here, though, is when you send samples in, you're going to get data back. And you have to think of this as sample data, not feed data. It doesn't necessarily represent the feed. It represents the sample. And very often you send a feed sample in, you get data. It's different from what you use to formulate the diet. But in reality, the feed didn't change. The sample did, but the feed didn't. But nutritionists see this new number, so they go to their computer, reformulate the diet. In this case, it's totally unnecessary. So you're paying for time to reformulate when you didn't have to. And there's a high risk that the new formula is bad, or will hurt milk production. So you need to make sure when the sample data change, you need to make sure, have high confidence that represents a true change in the feed. And the best way to do that is you take duplicate samples. And then the average of a duplicate is less likely to have sampling variation than a single sample. And a data I'm not going to show, when we took duplicate samples, we reduced the risk of bad reformulation by about 95% compared to single samples. So we almost eliminated that risk. On the other hand, if the sample data changed and you say, well, I don't believe it, I'm just going to leave things as it is. But if it really did change, if the feed really did change, you feed that diet for too long, you're going to lose milk or have other issues. So it's really important to know, don't ignore a change in composition, but make sure or increase your confidence level by duplicate samples that it really did, the feed really did change. And just some examples here, I'm just using protein and starch. Say the feed has less crude protein than what your sample came back, which happens about 16% of the time. I'm just going to say that happens about 16% of the time. So if you reformulate based on the new, or if you don't, if you reformulate based on the new sample data, your diet is not going to have enough crude protein. You will lose milk. On the other hand, if the feed actually has more protein than what your sample had, You overformulate protein, you waste feed dollars. For other nutrients, it might not be a big direct economic. For example, on starch of corn silage, say, if the feed has more starch than what your sample said, you could overfeed starch, have milk fat depression, sick cows. And if it has less starch, again, less energy, less milk income. So the bottom line is there is a huge cost to bad sampling. And bad sampling or inadequate sampling, because it can result in bad diets that have economic and health risk for the farm. So make sure you have good samples. I won't go into the protocols, but the key to sampling is you want the particles in this sample, the particles. And it's important you don't sample feeds, you sample particles. You want this blend of particles to represent all this. If you just go in, and you should never sample from a face of a silo because of health risk or a risk of dying. But if you just go in and grab a handful here and a handful here and here and here, that's the only particles you're going to represent in this bag. Whereas if you sample all this stuff that he's knocked down, these samples might represent this entire face. So we've written, if you're interested in this, we've written a couple preceding papers that go into sampling protocols, but it's worth taking 10 or 20 minutes to get a good sample. So what we came up with is for feeds that have high sampling error, and this is corn silage is the preeminent one, you need duplicate independent samples. If you're going to sample feed, take 2 of them, make sure they're independent. But you only have to sample it lately about once a month or even less. If you're working with feeds with high time variation, this is day to day or month to month, and this is more likely the hay crop forages, you need to sample more frequently, week to month, but you don't necessarily need duplicates, especially if you're taking following good protocols. The thing I want to move into now is TMRs. There's sampling of TMR has high sampling error, high risk. But there's also significant risk if it varies too much day to day, because this is what the cow gets. It doesn't eat just corn silage, it eats a TMR in most situations. And so first, let's go backwards. And that is why if you go to a farm and you sample a TMR today and sample it again tomorrow, why would it differ? Well, there is feeder mixture variation or error. This is largely controllable by good training and good mixer protocols. So this is controllable largely. It takes some work, but it's controllable. The composition of feeds is controllable, or I should be using the word manageable. It means you need to sample these feeds adequately and appropriately. But then there's this big chunk of observer variation. And this is what the cow doesn't see this. This is what you see. The lab will analyze things to get a little bit different results. And again, sampling is huge. So you control this, and you try to multiple samples, duplicate samples, and you try to get good estimates of this. Feeding a TMR, and the key here is well made. A TMR will be less variable in nutrient composition than the ingredients used to make the TMR. Here's an example. I put a very simple TMR together, 35 corn silage, 25 alfalfa, 40 concentrate. These are the NDF concentrations, the average of these feeds. This is for the diet. This is the standard deviation for NDF for these feeds. If I take an average weighted standard deviation and adjust for, it's a variance and do all the stuff correctly, the variation in the TMR is 3.1 on NDF, but this is wrong because this assumes dependency, that these feeds vary in unison. They do not. Corn silage today have above average NDF, but the alfalfa might have below average NDF. So these are independent. And that independence means that the variation of the mix is going to be less than the expected variation. We have software that generates these expected variations based on feed variation. And we'd only expect with these feeds, the TMR should have a standard deviation of 1.8, which is pretty good. So high variation feeds can be used in a well-made TMR, and it will reduce the overall variance because of independence. And again, assuming it's well-made. This is not an example of a well-made TMR. This is not, someone did not come in here and put this hay on the bunk. This came out of the mixer wagon this way. Obviously, this is going to be highly variable and worse than any of the ingredients. So you have to make a good TMR. And again, with training, good equipment, a good TMR is attainable. So another question we addressed here is, okay, how much variation can a cow take? And so we conducted a series of experiments. This is just one I'm showing with NDF. We had 3 treatments, and the treatments here was variation. Most nutrition experiments, the treatment is a mean. In other words, you test 14% protein, 16, and 18. We're testing variation. We had three treatments. The blue here is the constant. And you're going to say, well, it bounces up and down, but this is, you don't know how much trouble we went to get it this constant. We sampled feeds every day, we analyzed it every day, and we reformulated every day. So this is as good, this is better than anything you will ever see in the field. The average was 25% forage NDF with a little variation. The red bars are what we call the random variation treatment. Before the experiment, we used a random number table and generated these things. And basically what it says is on Monday, the diet's going to have 27% forage NDF. On Tuesday, it's going to be 21. On Wednesday, it's going to be 22. But this was a random pattern that all cows on that treatment were fed. And the green is a cyclic treatment. So we had 5 days of 26, then we switched 5 days of 24, 5 days of about 28, 5 days of 22. So a cyclic pattern. This might mimic someone reformulating incorrectly, but reformulating. The means we did not test, we were not testing the effect of 25% forage NDF. They all had the same. We tested standard deviations. The control had that's about 0.7, and again, that's very consistent. The other two were formulated to have the same variance at about 0.24, but remember, one is random day-to-day variation, the other is a cyclic variation. So variation, it was 4 times more variable in these two treatments, 4 times. On average, they were the same. And I've conducted research for 35 years, and this is the experiment that really, really surprised me. This is not what I expected. And what we found was absolutely nothing. Intakes, 25 kilos, no effect at all of treatment. We fed these treatments for 21 days. Milk, this was 10 years ago, so these are pretty good high milk productions. 42, 43 kilos a day, no effective treatment. Fat, 1.5 kilos a day, protein, 1.2 kilos a day. Absolutely no effect on milk production and production measures. The only thing we found was that for these treatments, the day-to-day variation in intake in milk was statistically greater than the day-to-day variation in the control. So cows responded to the diets, but it was so short term, 4 or 5 days at most, that it didn't matter to the cow. The cow could compensate. So variation, as long as on average you're about right over a short period of time, cows can handle a lot of variation. Okay, so that's what we've been doing. And now I'm going to switch gears, and this is where we don't have a lot of data, and that is the variation in requirements. Nutrient requirements can vary because of genetics, and you can have two cows producing the same milk, but are different genetically. They may have different requirements. Cows within a pen, you might have cows producing 35 kilos or cows producing 50 kilos within a pen. Those requirements vary day to day. It might be hot today, cold tomorrow, so on. So we'd expect some variation in requirements day to day. And then there's a huge, for some nutrients, there is a huge measurement error in obtaining the requirements. Most systems, software systems for dairy cattle still base requirements on the factorial system. Maintenance requirement, milk, lactation, growth, fetal, or pregnancy. They sum this. They divide by either an efficiency number. If this was energy, this would be the ME requirement divided by an efficiency factor to get the NEL, or an absorption coefficient if it's minerals. And there's variation in all these, and there's variation in these. We don't know a lot of the variations, but we know it's there. I'm going to use magnesium as an example here. The new magnesium requirement is a function for maintenance is intake times 0.3. We can measure intake on a farm or in research. And so the only variation in this would be measurement error. You can measure intake every day if you want. The 0.3 had a standard deviation of 0.05, which is pretty big. But we do know there's a lot of measurement error in this. Measuring maintenance requirements is very, very error prone. But there has to be some cow-to-cow variation, but we don't know what it is. But the overall variation is high. On the lactation requirement, it's milk, which again, we can measure on farm or in research, we can measure it every day. So the only variation here is measurement error. The average concentration of magnesium in milk is 0.11 grams per kilo. That has a fair amount of variation. This is probably mostly cow variation, not measurement. We can measure magnesium pretty well, but some of it is measurement, but most of this is cow. So we have reasonably good estimates of the variation for the lactation requirement. We don't have very good estimates on the variation in the cow variation in maintenance. And again, using magnesium as an example, the average absorption coefficient for magnesium for total diet is 30%. There's been enough studies, we can get a good estimate of the variation in absorption of 0.16. So 50%, the coefficient of variation here is more than 50%, huge. But with magnesium, we know some of the factors that affect absorption. Dietary potassium is a big one. Source of magnesium, whether it's magnesium oxide or feed or whatever. And feeding fatty acids, or the fatty acid concentration of the diet. So we can remove a lot of these sources and include equations to account for this variation. And that gets the standard deviation for absorption down from 0.16 to 0.05. Still variable, and some of this is measurement. But if we really know a lot, we can reduce the estimate of variation in availability coefficients. But again, we need to know this. For some minerals, we have no idea what the variation is. And especially the trace minerals, we have no idea how variable that is. Net energy, high measurement error. Maintenance energy is a high measurement. Diet does affect the maintenance requirement. We don't know how exactly. And of course, there's got to be genetics here. Some cows have to have a lower maintenance requirement than other ones. If same body weight, there just has to be. Moraes in 2015 published a paper, and this was a reevaluation of old data. But he came up with a mean maintenance requirement of 0.38 megajoules per kilogram metabolic body weight. But look at the variation, the 95% confidence interval. So if with a 650 kilogram cow, her maintenance requirement could range from 35 megajoules a day to 68. I'm used to calories, so 8 to 16 megacalories, twice. Huge, huge variation. The range here has the net energy equivalence of 12 kilograms of milk. So there's huge variation in requirements. And again, a lot of this is measurement error, but some of it has to be cow. Here are different papers showing these are calorie coefficients, not megajoule coefficients. But you can see on the low on one experiment was 0.85 times metabolic body weight, up to 0.16 times metabolic body weight. When we were doing the new NRC, we went through all this and put in 0.1 because it's pretty much the average. But we also discuss variation, and we show the variation in this. But remember, some of that variation, in fact, probably a substantial amount of that variation is measurement. So this probably is the best overall mean, but there is error or true variation. Now, what we don't know, and that is covariance among requirements. For example, I'm using calcium as an example. If a cow happens to have an above average calcium maintenance, her maintenance requirement is above average of what we would calculate. Does her lactate, does her milk also have higher than average calcium or lower than average, or is it not related? We have no idea. And if they're correlated, that could either reduce the total variation in the requirement or in the total requirement, or it could increase it. If they're negatively correlated, it would reduce the total variation in the requirement. If they're positively correlated, it would increase it. But we have no idea on covariance among these different requirements. And then is the absorption or efficiency factor which we use, is it correlated to requirements? The absorption coefficient almost definitely is. Just the way we calculate mineral maintenance requirements. It's an endogenous fecal requirement, and that's going to affect the estimated absorption coefficient. So for minerals, this correlation, it goes in opposite directions, actually is going to reduce the effective variation. But for other nutrients, we have no idea. So the question some of you should hopefully address in your career, and that is, how variable are total nutrient requirements? How variable is the ME requirement for a cow? Of a specific cow, if you put in a cow at 650 kilograms milk and 35 kilograms of milk, what's the ME requirement plus or minus what? We don't know. Same for calcium, copper, etc. We have no idea on the variation in the total dietary requirement, which is why we're stuck with using the means right now. So I want to end here on some recommendations. If you're formulating today, what can you do? We know things vary. What can you do? For minerals, if you take the requirement, and I'm going to say, let's use the NRC, the new NRC requirement. I think that's the best currently available, and I'm biased. It's about a 20%. We assume if we base it on other species, if you take the requirement, multiply by 1.2 and formulate to that, you will meet the requirements of most of the cows in that group. For MP, this was based on work we did a few years ago. You're formulating a diet. You take the average actual milk for the pen. Let's say it's 40. And the pen standard deviation for milk is 2 or whatever it is. You would want your maximum the maximum allowable milk to be actual milk plus 1 standard deviation. So on software now, it gives you an MP allowable milk. That should be 1 standard deviation above the actual milk for that pen, the maximum overfeeding. Right now, protein is extremely high. Milk is, at least in the US, is fairly reasonably priced, but still not as high as feed costs. So you'd probably want to be less than this maximum. And all these came up about through simulation requirements. For energy, you just feed to the average cow. That's because on average energy, if the average cow in a pen is overfeed energy, she's going to put on body condition that she lost earlier when she was underfed energy, and then use body condition score to moderate this. But minerals 1.2, minerals and vitamins 1.2, MP a maximum of 1 times the standard deviation, or 1 standard deviation in milk yield of the pen, and energy you formulate to the average cow. So in summary here, control what you can. Cows can handle variation, but control what you can. Make good TMRs, sample correctly, etc. Control what you can. But remember, observed variation is not the same as real variation. Observed variation includes lab variation, sampling variation. So make sure you can separate those out. Things might not be as variable as you think they are. And then lastly, in formulation, this overfeeding, you should never feed to the average cow, but the degree of overfeeding should be based on expected variation. And the more variation you control, whether it's grouping similar cows or good feed sampling and protocols, the less you have to overfeed. But you still always overfeed the mean, but as you control variation, you overfeed less. And with that, I thank you for your attention, and I'll be happy to try and answer any questions if there are any.
Thank you very much, Dr. Weiss, for the excellent presentation. So now is for question. So you can type your question through the Q&A. Dr. Weiss, we'll get the first question, the comments from Dr. Homan, the question. Sorry for that.
Okay, I'm reading. I got the question. I'm reading it right now. Do you want me to read it, or can everyone see the question?
Probably, yeah. You can read. Okay, yeah, you can read the question. Maybe be good.
Okay, I'm gonna summarize it a little bit. But he said, looking at this data, I just imagine how other often overlooked sources of variation, such as cow genetics, variation in the rumen microbiome, could affect feed efficiency, performance, economics. And where do you see the future of precision farming heading, and how could we integrate more of this into diet and farm management? That's exactly, we need to do this. If we're really going to get into precision farming, we need to start looking at how variable cows are, the requirements and the utilization of nutrients by cows. The way we get estimates of this is to do better jobs reporting it, and people need to start incorporating or trying to summarize all this variation. Like for example, I'm going to take some simple things. We have hundreds and hundreds of digestibility data, which can reflect the microbiome somewhat. Let's start with how variable is if I feed the same diet to a cow, how variable is the digestibility of energy? We don't know, but it could be done with the data handling systems we have now. That could be done. So I think people need to start, we need to, and this is being done now, we publish papers with means and standard deviations, but we have all this individual data, which is never, in the past, was never made available. Now, at least in the US, and I'm assuming in Canada, if you're getting public grants, you have to make all the data available. And so I think with this larger data sets with individual cow data and so on, people smarter than me in statistics can start start looking at the variation caused by cow, and that might lead eventually to more precise diets. So right now, I don't, other than data mining and people making all the data available so people can look at that, that's my only suggestion right now.
Dr. Weiss, I have one question for you about the requirement variation. You put the 1.2 times the requirement of the minerals, just 1.0 times for the energy requirement. So do you think the variation in the energy is not important to consider for the data formulation?
No, what I'm saying here is if I feed the average cow the average cow 20% more mineral than she needs. That's what I'm saying here. So I put on that, and I'm going to feed that average cow 20% more than she needs. That should meet, assuming cows are like rats, basically. But if they're like rats and have the same variation, that means almost every cow in that pen will be adequate. Most cows will actually be overfed, but there'll be very few cows that are underfed. With energy, half the cows are going to be overfed, half are going to be underfed. With minerals, if I overfeed by 20%, that has no risk. That's not going to hurt anybody. But on energy, if I fed 20% more energy than the average cow needs, that means most cows in that pen are going to gain condition. They're going to use energy. And that's going to mean at the end of a long enough period, the average cow in that pen will be over-conditioned, fat. Whereas if I feed to requirement, half the cows are going to be underfed. They will be losing condition, but eventually their milk yield will drop, and now they're going to start gaining the condition back. So that's why energy, I still say, you need to make adjustments based on condition score, but the average cow should be fed the right amount of energy to avoid too thin or too fat. Whereas minerals, overfeeding, because either the excess mineral won't be absorbed because of downregulation, it'll be excreted in urine, or it may be retained, but for macro minerals, there's very little risk. That's the reason. It's not saying this is less variable. It's just saying there's more risk if you consistently overfeed energy.
Yes, thank you very much. Yeah, if you have more questions, okay, from Dr. Marcus Cadero, very interesting presentation. Could you comment on the potential of the analytical techniques such as NIR to reduce the variation?
Well, NIR pretty much eliminates lab variation, because you're going to get, if you rescan things, you get essentially the same number, but that's not that important. NIR, if it's done correctly, to me, it makes the analytical cost low enough where you can afford to take enough samples. So I think NIR will help reduce sampling variation, because again, you can afford to take duplicate samples and you can sample more frequently. So NIR, I don't think it's helpful because it's cheaper than wet chemistry analysis. And, people don't like to spend a lot of money. And if NIR cuts analytical cost in half, they may, instead of sampling, that may encourage people to take twice as many samples. And that helps reduce sampling variation and adjust diet formulation. There's some suppliers will have actually on-farm NIRs where, you buy an NIR and you could sample feeds every day. At this point, I'm a little leery on that because, these major labs will have calibration equations based on a million samples, maybe. Their calibrations are very, very good. But on a single farm, you know, your calibrations may not be so good. So I'm a little leery right now of on-farm NIR. I'm very much in favor of commercial lab NIRs, because again, it should encourage more sampling, more analyses.
If you have more questions, please type your question from the Q&A. Dr. Weiss, I have another question about it. You use the crude protein safety factor 1.8. I just wondering how you got this number 1.8, just based on the study or based on your own experience, or?
It's based both on statistics, on distributions, and some simulations. We collected a lot of variations, a lot of standard deviations. Then we'd sit and simulate diets, just simulate diets. And if anyone's interested, I have a Excel program that'll do that. And our goal was to say, we wanted to have the same risk as if you fed very consistent, corn, if you had a diet with corn grain, soybean, minerals we didn't really include, very good consistent corn silage. But in other words, we said, how variable is the best we can do using consistent feeds? And then we'd simulate with these variable diets how we had to adjust it to get the same risk of a deficiency. So it's based on mostly simulation. And 1.8 was where 1.8 times inclusion rate came up where the risk was similar to this consistent diet. The risk of a deficiency was the same as a consistent diet.
Yeah, thank you very much. Yeah, we still have more time for questions. Please type your questions through the Q&A. Okay, there. Question from Dr. Martin Nacharti. Excellent presentation. You stated that cows can handle a lot of variation. Is that because they are draw on the body reservoirs or change the efficiency with which they utilize the nutrients?
Okay. Well, I think it's a few things here. One is, we as nutrition researchers, we do everything basically day to day. We measure milk every day, we measure intake every day, etc. But if I change the diet on, if I feed a diet on Monday and I make a diet change on Tuesday, at least a third of the diet I fed on Monday is still inside the cow. So just the capacity of the GI tract and the rumen buffers some of this day-to-day change. And then the other thing, what you mentioned about reserves, is I really think it's mostly a reserve thing. And in this study that I cited here, we measured a lot more than what I talked about. And on those days, when I'm going to just back up here so you just see. On these days when we fed very high forage NDF, the cow ate less. And then on some measurements we did, that it indicated that cow, when she ate less, increased body mobilization. So there was data that she increased energy mobilization, fat. So I think a lot, and we know on electrolytes, for example, they can do that. So I think it's in the short term where we see this day-to-day short-term variation. I'm guessing most of the buffering is in reserves, not in a change in efficiency. Long-term, it might be inefficient. For example, with minerals, if many days I feed a calcium deficient diet, she's going to upregulate absorption, increase what I'm calling efficiency. So I think over longer times, the cow can moderate variation through efficiency changes, or at least moderated somewhat. But day to day, I think a lot of it is reserves. And again, a lot of it, some of it is the fact that, you know, there's the rumen and the intestine still have about at least a third of the diet she ate yesterday inside her. So
another question from the Yan Xing Liu, great presentation. As in the presentation, discount factor for the crude protein and the macrominerals is 1.8. So how about other nutrients?
The reason we're limiting it right now to protein and macro minerals, and again, I want to be clear, this 1.8 was an example. You know, it varies depending on inclusion rate. But the reason we use that for crude protein and macro minerals, again, is the main risk with protein and macro minerals is deficiency within reason. In other words, overfeeding protein has an economic cost. The diet's more expensive, but it doesn't hurt the cow. And the same with most macro minerals. It doesn't, within reason, overfeeding does not hurt the cow, but a deficiency will. But for these other nutrients, there's a much narrower range between good and bad. And let's take starch, for example. If you want to feed a 26% starch diet and you have a highly variable feed and you do my discount, the average diet is going to be higher than 26% starch. And that increases the risk for acidosis. It reduces the risk of being energy deficient, but it increases the risk of acidosis. And so for other nutrients, the nutritionist really has to decide what risk does he want to take. Does he want to reduce the risk of deficiency? Then you would apply that discount. But if on the other hand, you say, well, I want to make sure I don't overfeed this nutrient, then you do just the opposite. And if you're going to say, well, I want to keep the risk of over and under feeding the same, you don't discount anything. So these other nutrients, it's up to the nutritionist to say which is worse, a deficiency or an excess. But for crude protein and macro minerals, their deficiency is almost always worse than overfeeding. That's why we limit it to just those two nutrients.
Thank you. Now, any more questions? So, Dr. Weiss, do you mind asking my last question? So, because our colleague and the students are monogastric nutritionists, so the best your experience with the handling the variation in the daily cow nutrition, do you have any suggestion for the monogastric animal nutritionist how to handle the variation?
It's be very similar. They have, I'm going to say, not the non-ruminant nutritionists have it easier than us. One is their feeds generally are less variable than our. They don't have to feed forages, and corn and soybean meal are pretty consistent. And I think they also have they can do much larger studies than we can. So I think they have better variation or estimates of variation in requirements. And so they can apply the same principles, but the effects, the diets are going to vary. In my opinion, their diets will vary much less than ruminant diets, and the animals are going to vary much less than that. So all this I think would be less important for it's still, I don't want to say it's not important, but it's going to be less important for those species than our species, our ruminants.
Yeah, thank you. The question from Dr. Marcus Cadeno. Some people have talked about the animal level management. Should this be encouraged based on the fact that the animals can handle the variations?
The animals can, we've done studies and there's been a few more people looking at this since we published this, but we still need more data. But the only nutrients we've looked at The effect of variation is forage NDF, this experiment here in Journal Dairy Science. We did a study with fatty acids, and we've done a few studies with crude protein. And in this study here, the average, which, this is huge variation, but the average diet was formulated to be 25% forage NDF, which is quite high. And we did that on purpose because I was really worried about sick cows. And they handled this fine. But, in the real world, you might be down here, closer to the edge. And then if you have that same variation, you might have a lot of sick cows. So I don't want you to overinterpret that variation doesn't affect cows. The stuff we've studied so far has not had a huge effects, but again, we overfed forage NDF in here. So animals can handle more variation than we think, but we need more data with more nutrients under more situations before we say they can really handle variation. So I still think we're getting better. We have technology now where we can measure things on individual animals in groups, the rumen boluses, the rumination monitors, all this stuff. So that will help on this, but I want to caution people to don't leave here thinking that cows variation does not affect cows. For some nutrients, it doesn't. For other ones, it might. And the experiment, if I had not retired, the experiment I would have tried to get through animal care is doing starch. And starch, our diets are very often 28% starch. And I would have loved to do that. I'm thinking we would have got sick cows, because on these days when starch was 32%, I think we'd have gotten sick cows and it would have been bad. So if you're young, think about doing some of these studies so we get better data. So I know I didn't really answer your question too well, but variation might affect cows more than this one study shows.
Yeah, thanks for the question. Everyone raised the question, and I think because the time interest, so please join me. Thanks, Dr. Weiss, for the excellent presentation. So I have learned a lot. I'm sure that our audience has learned a lot from your presentation. Yeah, very much appreciate.
Thank you, and I'll make these slides available. I can go ahead and say I think I've already sent them to you. Feel free if someone wants them to distribute them. It'd be no problem on distributing them.
Yeah, very much appreciate for that.
And thank you again for the invitation.
Yeah. Have a good day, everyone. Have a good day, Dr. Weiss.
Okay. You too. Thank you very much. Goodbye.
Bye.